Reservations in two-way slabs by means of yield lines. This video will deal with case 9 as type of reservation, and the characteristics of the slab is that one side is fixed and the other three sides are simply supported. Orange means simply supported. The green means a slab is continuous or it is fixed on a wall or a column. So we will now take care of case 9, which is a centric reservation hole which is attracting the yield lines. We will explain it just now what that means. So we have case 9 now. In normal cases, when you have a two-way slab, then we can estimate where the yield lines are, and we use for that the 60, 45, 30 rule. It means when one side is fixed, that's 60 degree, the other side is 30 degree. 45 when both sides are equal. So that's a 60, 45, 30 rule. When you have a central reservation like this into the slab, you will see that the yield lines are very strange then. This in the middle disappears because it's a cut, it's a slab is a reservation, and then the yield lines will do like that. This is not a yield line which is realistic. So what we now can do is that the corners of the reservation will attract the yield lines. And so the yield line will go directly to the corner of the reservation to the corner of the slab. So the rule of 60, 30 degrees does not apply here. It is just straightforward. This, when the reservation is big or very centric, then is a more realistic view of yield lines than this. So we will see later on how we can choose between the two. But for a centric reservation, we will use tracking yield lines instead of the 60, 45, 30 rule. So now let's start. This is the slab with side A and B smaller than 2 times A. We have the reservation in the slab with dimensions D2 and D1, and the slab is centric. So the D4 on this side is the same as the D4 here, and D3 on this side is the same as this. This is what is meant by centric. Then we draw the yield lines, which are of course from corner of the reservation to the corner of the slab. This is the most realistic yield line. So if this is overloaded, that will be the where the cracks appear. And of course, where the slab is fixed, there's also a yield line. The conditions for case 9 is then two-way slab A must be smaller than B, smaller than 2A. The maximum hole size, of course, is that D1 must be smaller than A and D2 must be smaller than B. That's obvious. And then because of the symmetry, because of the centric hole, we make that D4, that this D4 on the left, on the right-hand side is the same as on the left, and in the other direction also the same. This is this equation. So in fact, we have D3, D4, D1, and D2, and A and B as parameters. These are the different conditions. Again, now what does that give in reality? Well, you have different cases of centric reservations attracting the yield lines. You can have this or that or this. Now we must take care that when this centric hole is approaching the support of the slab, it's getting a little bit, you get a situation which is not realistic in real life. So in fact, we should always keep a certain distance from the support when you have a centric hole attracting yield lines. But first we'll try to calculate the maximum bending moment in case 9. The work done by the external forces are then equal to, we have d4 times d3, which is the surface of this, d4 times d3, which is the surface of the green colored elements, which consist out of 2 triangles, and on the 4 corners it's the same. So we have 4 times 2 d4 times d3 multiplied by the mean deflection, which is delta over 3. And then for the rectangular elements, we have d3 times d2 and d3 times d2, and we have d4 times d1, and we have that one here, one's there, one's here, and one there. So you have it 2 times d3 times d2 plus d4 times d1, and the mean deflection is delta over 2. You can simplify it by using this formula. We know that d4, because it's centric, and d3 is this element. So we can now make this approach, of course. The work done by the internal forces or bending moments is then equal to its first those 4 yield lines. It's d4, which is the length of the yield line projected on this axis. So it's d4 times the angle. It's delta over d3. So that's d4 divided by d3 times delta. And then on the other side, we have d3, which is this yield line projected on this axis. So it's d3 times the angle of rotation, which is delta over d4. And we got that 1, 2, 3, 4 times. This is the 4 plus the yield line on the fixed side, and it rotates over delta over d3. So d times delta over d3. Then we fill in d4 and d3, and then you got this equation. You see me. Okay. Now the bending moment is then when d is equal to E, and when you do the calculations, you arrive at this formula. You see that when A equals D1 or B equals D2, then the bending moment is 0. It means that it's a little bit foolish to calculate that. Now we can work with dimensionless units. dy is alpha y times A and B is alpha A. The bearing capacity is defined as 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole, or it is the maximum load with the hole divided by the maximum hole without the load. So the maximum moment without the hole is m0 divided by q gives you this formula. The bearing capacity is then a function of alpha, alpha 1, and alpha 2, which is the size of the reservation, and alpha is the dimensions of the slab. So when we rework this, then you have this type of formula. You see again that when alpha is equal to alpha 2, this goes to infinity, it's not right. So what does that mean? Alpha means it's 2 times A, and alpha 2, it's D2 divided by A. So it means that B will be bigger than D2. So that when this is happening, then this is not working right. But you see if D2 is equal to B, then you got this type of reservation. But this type of reservation means that this gets to 0 and this to infinity. So we must exclude this. The same for alpha bigger than A bigger than D1 is also not possible, but when D1 is equal to A, we get that time of reservation. So we will not deal with that because you divide by 0. So now we look at the bearing capacity in function of the geometry of the slab. So alpha is B times A. And we know that alpha is between 1 and 2. And here we have chosen as an example that D1 is in fact 0.2 times A. And it's for a D1, which is always 1/5 of the smallest dimension of the slab. And in those cases, we vary the length of the reservation, which is D2, by 0.2, 0.4, 0.6, and 0.8. Then you get those different curves. Let's look at this point. We calculate the bearing capacity for this point because it's 1.6 as dimension of the slab. And we are talking about 0.2 of the size of the reservation, and it's a square size, so it looks like that. The 1.6.2 and 0.2 looks in fact like that, and it gives you a bearing capacity of 102. So it means that making a hole or a reservation in the middle of the slab, you in fact do not change the bearing capacity of the slab. Instead, theoretically, you augment it because this load disappeared. Then we can have a second look on the blue dotted line, where then the blue dotted line is where D2 is 0.4. So you see, I keep the smallest dimension of the reservation as 0.2, and I keep the 1.6, and then the other dimension is 0.4. So you get a reservation like this. And then you see that you lose bearing capacity. So once you go bigger than a certain value of the hole, in the beginning it does not touch the bearing capacity, but when you make the hole larger and larger with the same width, you lose bearing capacity. So, and this is demonstrated by those curves. Now let's take another look at it. Now we will keep the alpha equal to 1.5. So B is 1.5A. And we look at different cases where alpha 1 is from 0 to 0.6. So what I do is I leave a gap of 1/5 of the slab around the edges of the slab for not having a non-realistic results. And then it's all in function of the length of the reservation. We noticed directly that for 100%, so the bearing capacity is not touched, that between those two values for this reservation, a reservation of 0.2, that you have a maximum or a minimum of bearing capacity, and outside you augment the bearing capacity. So those 2 points are interesting. When we look at those 2 points, so in the blue dotted curve, it's 1.5 times 1.50202. So this is 100% bearing capacity, does not change the bearing capacity. And then when you make the low very large, which is this, then you also have 100%. So that are those 2 points. So between this gap or this reservation and this reservation, you lower the bearing capacity of the slab, and outside you do not lose bearing capacity. Then we can look at the third point where the bearing capacity has a minimum, so it's you lose 10%. So this type of hole gives you 10%. So if you make a hole, do not use this one, but use this or this, not this one. Oh, alpha 2 is of course between 0 and 1.1. Why not 1.5? Huh? because you have around the edges, you will have 1/5 of the smallest diameter that you will not touch. You will not make a hole bigger than that. And alpha 1 must be between 0 and 0.6, the same reason. So we can now put the bearing capacity in a graph to understand a little bit more. The x-axis is alpha 2, which is the longest side of the reservation. And the bearing capacity, we draw different curves for different geometries of the slab, B over A, and with a fixed value of the smallest size of the reservation, which is 1/5 of the smallest size of the slab, and that all in function of alpha 2. So you can see here, for instance, at this point, that for a slab with B equals 1.2 A, that's the green line, and for the smallest size of the reservation or the hole is 0.2, then we end up in 96% of bearing capacity. So you lose 4% of bearing capacity by making a centric hole of this size, of this type. This is what this curve means. Now we can look at the red curve for a square slab. You see that for alpha 2 equals 0.3, that we end up with 94% or something like that of the bearing capacity, so you lose 6%. And finally, we show that for instance, this dotted green curve is almost straight. That's for a slab with the largest side of the slab is 1.5 times the smallest, with a reservation of 0.2 times 0.6 times A, gives you this point here, bearing capacity loss of 9%. So you can play around with all those types of curves to find the relationships between the bearing capacity and the size of the hole. Now, let's take a square hole in a square slab. One side of the slab is fixed, the others are simply supported. We know that D1 is equal to D2 because of the square hole. And alpha 1 is smaller than 0.6. That means that around it, you always have at least 0.2 times A free space. So the reservation cannot be bigger than this, what I'm mentioning in now. Cannot be bigger than that. Why? Because otherwise you do not have realistic yield lines. The slab will not behave like we are thinking it should behave. With those data, the bending moment is a function of A, because B is equal to A, and of D1, because D2 is equal to D1. So this is the maximum bending moment for a square slab, of a square hole in a square slab. We can make a graph of it, and we can go directly to the bearing capacity. On the x-axis is the size of the reservation. Again, from 0 to 0.6. Not, in fact, it should be from 0.2 to 0.6. But okay, that's fine. Then the bearing capacity, the function, when you divide everything, you make everything dimensionless, like for instance D1 divided by A and A divided by A, you arrive at this dimensionless formula, and then you see that this is the relationship between bearing capacity and the size of the hole. And what is interesting is that you have a point where when the size of the hole is 0, it means there is no reservation. Then of course the bearing capacity is 100% by definition. But you also see that when the bearing capacity of is 93.6, when the size of the hole is 0.172 times the size of the slab, which is that point there, the minimum. And again, we have for 0.347, we have a bearing capacity equal to 100. So again, we have the situation when You start with no reservation, it's 100%. You make the reservation bigger and bigger until you reach the point of this. And after that, the bearing capacity will increase. So the size of the hole, just think carefully what the size of the hole will be that you make. So we can conclude that the bearing capacity is smaller than 1. So it means that that is okay for the slab, for existing slabs, for instance. Then the size of the hole must be between 0 and 0.347 times A, this size, which is this point there.